The kinetic theory of gases is a fundamental scientific model that describes the behavior of gases at the molecular level. It provides a framework for understanding how gas particles move and interact with each other, leading to the macroscopic properties of gases, such as pressure, temperature, volume, and density. This theory is based on several key postulates. Gas consists of tiny particles. The theory assumes that gases are made up of a large number of very small particles, such as atoms or molecules. These particles are considered to be point masses, which means they occupy negligible volume compared to the volume of the gas. Constant, random motion. Gas particles are in constant, random motion. They move in straight lines until they collide with other particles or the walls of the container. The collisions are perfectly elastic, meaning there is no net loss of kinetic energy during collisions. Negligible intermolecular forces. In the kinetic theory of gases, it is assumed that the interactions between gas particles are negligible, except during collisions. This implies that the attractive and repulsive forces between gas particles are much weaker than the kinetic energy of the particles. Conservation of momentum. The total momentum of the gas particles is conserved in the absence of external forces. This means that the sum of the momenta of all the gas particles remains constant over time. Average kinetic energy is proportional to temperature. The average kinetic energy of gas particles is directly proportional to the absolute temperature of the gas. This relationship is expressed by the equation, Ke equals 3/2 kT, where Ke is the average kinetic energy, K is the Boltzmann constant, and T is the absolute temperature in Kelvin. These postulates help explain the macroscopic properties of gases. The kinetic theory of gases is a powerful tool in understanding and predicting the behavior of gases under various conditions. It provides a solid foundation for the study of thermodynamics and plays a crucial role in fields such as chemistry, physics, and engineering. The kinetic theory of gases is based on a set of fundamental assumptions that serve as the foundation for understanding the behavior of gases at the molecular level. These assumptions help explain how gas particles interact and lead to the macroscopic properties of gases. The key assumptions of the kinetic theory of gases are as follows. Gas consists of a large number of tiny particles. Gases are composed of a vast number of very small particles, which can be atoms or molecules. These particles are considered to be point masses, meaning they have negligible volume compared to the volume of the gas as a whole. Gas particles are in constant motion. The particles in a gas are in continuous, random motion. They move in straight line paths until they collide with other particles or the walls of the container. The motion of gas particles is characterized by their kinetic energy. Collisions are elastic. When gas particles collide with each other or with the walls of the container, these collisions are perfectly elastic. In an elastic collision, there is no net loss of kinetic energy. The total kinetic energy of the gas particles remains constant, although individual particle velocities can change. Negligible intermolecular forces. The kinetic theory assumes that the interactions between gas particles are negligible except during collisions. This implies that the attractive and repulsive forces between gas particles are much weaker than the kinetic energy of the particles. Volume of gas particles is negligible. The volume occupied by the gas particles themselves is considered to be negligible compared to the total volume of the gas. This assumption allows us to treat gases as continuous substances rather than discrete particles. Average kinetic energy is directly proportional to temperature. One of the key insights of the kinetic theory is that the average kinetic energy of gas particles is directly proportional to the absolute temperature of the gas. This relationship is expressed by the equation, Ke equals 3/2 kT, where Ke is the average kinetic energy, K is the Boltzmann constant, and T is the absolute temperature in Kelvin. These assumptions provide a simplified model for understanding the behavior of gases. While they are idealizations and may not fully capture the behavior of real gases under all conditions, They are remarkably effective in explaining and predicting the behavior of many gases in everyday situations and in many scientific and engineering applications. The kinetic theory of gases serves as the basis for the ideal gas law and plays a fundamental role in the study of thermodynamics and gas behavior. The law of equipartition of energy is a fundamental principle in statistical mechanics that describes the distribution of energy among different degrees of freedom in a system. It applies to systems in thermal equilibrium and assumes that each degree of freedom contributes equally to the total energy, on average. The law can be expressed mathematically as follows. For a system in thermal equilibrium with temperature T, each degree of freedom contributes 1/2 kT to the total energy, where K is the Boltzmann constant and T is the absolute temperature in Kelvin. Now, let's apply the law of equipartition of energy to specific heats of gases. Monoatomic gases, e.g., noble gases like helium, argon. Monoatomic gases have 3 translational degrees of freedom, X, Y, Z, and no rotational or vibrational degrees of freedom. According to the equipartition of energy, each translational degree of freedom contributes 1/2 kT to the energy. Therefore, the molar specific heat at constant volume, CV, for a monoatomic gas is given by CV equals 3/2 R, where R is the gas constant, R equals kNa, Na is Avogadro's number. Diatomic and linear polyatomic gases, e.g., nitrogen, oxygen, carbon dioxide. These gases have 2 additional rotational degrees of freedom, about 2 axes, in addition to the 3 translational degrees of freedom. Therefore, each molecule has a total of 5 degrees of freedom. According to the equipartition of energy, each degree of freedom contributes 1/2 kT to the energy. For a diatomic or linear polyatomic gas, the molar specific heat at constant volume, CV, is given by CV equals 5/2 R. Non-linear polyatomic gases, e.g., water vapor, carbon dioxide. At higher temperatures, non-linear polyatomic gases have 3 rotational degrees of freedom, about 3 axes, in addition to the 3 translational degrees of freedom. Therefore, each molecule has a total of 6 degrees of freedom. According to the equipartition of energy, the molar specific heat at constant volume, CV, for a non-linear polyatomic gas is given by CV equals 6/2 R equals 3/2 R. These expressions for specific heat, CV, based on the law of equipartition of energy, are valid at temperatures where classical mechanics is applicable. At very low temperatures or for light atoms at high temperatures, quantum mechanical effects become significant, and the equipartition theorem may not accurately predict specific heats. Quantum mechanics provides a more accurate description of specific heats in these cases. The Maxwell distribution of speeds, or Maxwell-Boltzmann distribution, is a probability distribution that describes the distribution of speeds, magnitude of velocities, of particles in a gas at a particular temperature. It is a fundamental concept in statistical mechanics and plays a crucial role in understanding the behavior of gases. The distribution is named after James Clerk Maxwell and Ludwig Boltzmann, who made significant contributions to the kinetic theory of gases. The Maxwell distribution of speeds is characterized by the following key features. Shape of the distribution. The distribution is a probability density function that depends on the temperature of the gas. It is a bell-shaped curve, similar in shape to a Gaussian, normal, distribution, but with a long tail extending to higher speeds. The peak of the distribution corresponds to the most probable speed of particles at that temperature. Dependence on temperature. The distribution's width and shape change with temperature. As the temperature increases, the distribution becomes broader, meaning that there is a wider range of speeds at higher temperatures. The average speed of the particles also increases with temperature. Peak of the distribution. The most probable speed, Vp, corresponds to the speed at which the maximum number of particles have that speed. It can be calculated for a given temperature using the following formula: Vp equals square root 2 kT/m, where Vp is the most probable speed, K is the Boltzmann constant, T is the absolute temperature in Kelvin, and m is the mass of the gas particles. Average speed. The average speed, VAV, of gas particles can also be calculated, and it is greater than the most probable speed. It can be expressed as VAV equals square root 8 kt/m, root mean square speed. Another commonly used measure is the root mean square, RMS, speed, denoted as VRMS, which is calculated as VRMS equals square root 3 kt/m. The Maxwell distribution provides valuable insights into the behavior of gas particles and their kinetic energy distribution at a given temperature. It helps explain various properties of gases, such as pressure, diffusion, and viscosity.